In this video, we present how a sequence can arise from a mathematical model. The mathematical model we consider here is a demographic model, which is a kind of model used to describe the evolution of a population. What is the nature of the population is not important. The population could be a population of individuals, humans, say, or animals, or viruses, or bacteria, or many other things. It doesn't change what we say here. The simplest possible demographic model is the Malthus model. This is the simplest possible model because it makes a certain number of extremely simplified assumptions on what is the behavior of the population. Let's see how this model works. As for every other demographic model, the key quantity we want to study is Pn, the size of the population at time n or at the nth generation. And the key ingredient is what is called the growth rate of this population. Let's see what is this quantity. Now, if you want to study the evolution of the population, you want to see how Pn changes with n, you will be interested in variations of Pn. So in quantities like this, Pn plus 1 minus Pn. This quantity represents how Pn changes from time n to time n plus 1. So for example, if this quantity is positive, it tells that the population has grown from time n to time n plus 1. Vice versa, if negative, it tells that this is smaller than this, so the population has reduced. However, the numerical value of this is not necessarily telling us what is going on the population. Let's see why. Imagine that I tell you that this variation is of 1 million of units. The first question you may ask me is, yes, but 1 million respect to what? And that's the right question, because if I have that the population has grown of 1 million of units, and the initial population was of 1 million of units, it means that the population has doubled. So the growth is about 100%. Plus 100%. If, however, I say that the growth is of 1 million of units over a population of 1 billion of units, now there is a growth, yes, of 1 million of units, but it is much smaller because now it is about 0.1% over the total. That's why it is important to compare this quantity to the size of the population, so to consider this ratio. Pn plus 1 minus Pn over Pn. Now this quantity is what is called the growth rate of the population. It is normally denoted with a letter like R, and normally it will depend on many factors. Just to simplify and to show examples of these factors, we may say that there are at least two factors could affect this R. First of all, R could depend on n, so on time. Imagine we are talking about a human population, and there is a war that you cannot predict, is something that happens at a certain time, or there is a climatic change, which is an actual problem. This will affect how the population reproduces and grows, because, for example, there is no more enough food, or conditions are such that people die just because of a war, for example. So this is a first variable that enters in the growth rate. Another quantity that could enter in the growth rate is the size of the population itself, because you may imagine that higher is the size of the population, the lower will be the value of the growth rate. For example, if we have a big number of individuals, there will be less food for everyone. So not everybody will have enough food to survive, and so someone will die because there is not enough food. So this is, let's say, an example of what could be the key ingredient. Of course, in a real problem, there could be many other factors here. But let's stay on these two. Malthus model assumes that this growth rate is the simplest possible. So it's just a constant. So something that is not depending on n and something which is not depending on the size of the population. Under this assumption, we can easily figure out what is the value of Pn, because if you look at this identity, we can also rewrite Pn plus 1 minus Pn equal R0 Pn, or in other words, Pn plus 1 equal 1 plus R0 Pn. You see that this is a recurrence relation that gives the value of Pn plus 1 given the value of Pn. You can now work out details and show that from that relation it follows that Pn can be expressed explicitly in its dependence on n. So Pn turns out to be equal to 1 plus R0 to power n times P0. I warmly suggest you to do this calculation to show that this formula holds. From this formula, we have main information. So first of all, we have the dependence of Pn on n, and we can see what happens to this quantity in time, so when n goes by. For example, if you start considering examples like take fix R0 equal 1, you see that here you get 2 to power n times P0. So with this growth rate, the population basically doubles at every generation. With R0 equals 0, we have easily that this parenthesis is 1, so 1 to power n is 1, and Pn will be always equal to P0. So we have a constant behavior, nothing changes. If R0 is negative, for example, minus 1/2, 0.5, plugging this here, we get that in the parentheses we have 1/2 to power n. And so Pn will be 1/2 to power n P0. In this case, we see the opposite of the first example. Population halves every time. So let's say that in general, these three cases are the three cases. We have a case when the rate is positive, the population grows here, it is represented the value, numerical value of Pn as function of n, which is on the horizontal axis. So this is Pn in function of n when r is positive. When r is 0, it is constantly equal to P0. And when r is negative, actually this r can be between -1 and 0, cannot be less than -1 for this model. You see that P0 is decreasing and going rapidly to 0. So this figure tells that basically Malthus model gives three possible predictions for a population, or either an exponential growth, never-ending exponential growth, or a constant stationary situation, or an exponential decay to 0. That means the population is going to the extinction. As you may understand, these three behaviors cannot be the behavior of a complex population. Let's imagine that we use this model to describe the time evolution of the human population on our planet. We cannot imagine that the population is growing forever because there is not enough physical space. This physical space is finite, so we cannot have any number of people on the planet, and there is no food. We cannot expect that this behavior is the behavior of the future population on our planet. This is an extremely particular case, and the other possibility is that the population is going to the extinction. So it's a very simplified model. Other models, they capture more complex behaviors, and we will present another example of this model, which is the logistic model, in the next video that I suggest you to give a look.